Hello, this is Peterson again. This is the third installment of the module on model evaluation. We've talked about some general concepts and we've talked about the practicalities. Essentially, we've used the confusion matrix to look at some metrics of performance. Now we're going to talk about significance tests. I'm not going to give you the full gamut of tests that have been applied to testing model predictions in niche modeling and distribution modeling. Rather, I'm going to give you essentially three methodologies that are quite simple, but that are very commonly used in the literature. And my idea is that with these three example methodologies, you'll be able to comprehend, understand the different methodologies that you see out there in the literature. So let's imagine a map. Okay, again, latitude, longitude, just like in our last module. And on our map we have a prediction that covers about 10% of the area. Okay, essentially what I want to do is show you some very simple methodologies to a situation like this. So this is a binary map. Okay, this is a map in which everything is either predicted present or absent. And we'll talk about in another module the idea of thresholding maps, thresholding model predictions to yield binary maps. For the moment, let's just imagine that we have a binary map, and so we're going to call this this set of approaches threshold dependent, because they depend on setting some critical threshold for what is presence versus what is absence when you have an otherwise continuous output. Now let's imagine that we take our independent evaluation data and we overlay them on this prediction. And in a very good world, maybe we get that. So you see we have 10 testing points, and of our 10 testing points, 9 of them fall inside the prediction. And so essentially what we're asking is a cumulative binomial probability that we can get 9 successes out of 10 trials when the underlying probability of a success is 1 in 10. And I did this calculation, and the probability is quite low. In fact, it's less than 1 in 1,000. Okay? So essentially what we're saying is that this particular model seems to have good predictive ability when it comes to anticipating the distribution of our independent testing data. Now let's imagine another situation with a different set of testing data. Again, we have 10 points, but here we're saying what's the probability of getting 1 success when we have 10 trials and a probability of 10%. And essentially this is going to be a p around 0.5, which is to say this is a non-significant prediction. And so in the case of the blue occurrence points, our model really had no significant explanatory power about where those points would fall. In the case of the red occurrence points, indeed our model had some predictive ability. Now, this is a very simple case. This is a case of where we have a binary model. Most model outputs are not binary. Most of the algorithms that you'll use for predicting distributions and characterizing niches instead give you a continuous surface. So let's draw another map. And maybe we have an area of high predicted suitability, and then some surface of lower and lower predictive suitability down to some lowest level. Okay? That's more common. Essentially all of the algorithms that are in vogue right now produce such a continuous surface. Now here we can't use just a simple binomial approach. Why not? Because where does it stop being suitable as we go from high to low? We'll give you another module in this curriculum that treats the question of thresholding. For the moment, let's leave that question aside and let's ask some questions about how do we evaluate models without making assumptions about thresholds. And so we can call these threshold independent approaches. Now, let's again overlay some independent data. Okay? Now what you can see is that most of our points are in the areas of higher suitability. Another data set, just like in the last example, another data set might be all over the map. But now we don't have that simple equation of the binomial probability distribution. So one thing that you'll see very commonly in the literature is what's called a receiver operator characteristic. And it's a graph of what's called sensitivity, which, by the way, is 1 minus the omission rate that we just discussed. And so it's graphing sensitivity against 1 minus specificity. And guess what? 1 minus specificity is equal to the commission error rate that we just discussed also. So these are familiar quantities to you. Both of them go from 0 to 1. And that's actually a very important point. The line of random expectations, essentially the performance of a random classifier, if we were just to use unrelated predictions and test data, it would be a diagonal line like this. And so, because each of these is scaled from 0 to 1, the area under this line, we'll call it the area under the curve, equals 0.5. That's for a random classifier. Now, our blue data are pretty close to random, and so the blue, the bad model predictions are going to look like that. In the case of the red data, notice this. In a very small area, we accumulate lack of omission, which is to say most of the points are clustered in a very small area of high suitability. So our model accumulates lack of omission, it avoids omission in a very small area, and then eventually turns and comes up to 0 omission. So this curve is going to have an AUC that's pretty high, maybe, I don't know, 0.9. The blue curve is going to have an AUC that's near 0.5, which is to say that's near random expectations.